Okay, let's review what you should have read about the dot product. So, given two vectors, and for the sake of ease, we're going to restrict ourselves right now to 2 dimensions. So A will be equal to A1, A2, and B will be equal to B1, B2. And so we defined the dot product between two vectors to be the sum of the product of their components. So it will give us a scalar, A1 times B1 plus A2 times B2. And so that is not a vector, it produces a scalar. Okay, easy enough. If I gave you 2 vectors, I am certain that you could find the dot product. The definition extends if we have, if we're in 3 space, it's just our dot product becomes A1B1 plus A2B2 plus A3B3. So it's easy enough. Now, you should have read about the properties, and it's a good exercise for you to prove those to yourself. I'm going to list a couple that we use a lot. One is that A dotted with itself is the magnitude of A squared. That comes up a lot. We know that, and that's easily seen, that the dot product is commutative. So I can dot A with B or B with A and I should get the same thing. It is also associative. It distributes over addition. So A dot B plus C. So if I sum 2 vectors and then which produces a new vector, and then I dot that with a vector A, I get the same thing as if I dot A with B, I dot A with C, and I sum that up. Easy enough. 4 is that if I take a constant times my vector A, so I scale it, get a new vector, and dot that with B, that's the same thing as if I take A and dot it with that same scaled factor of B. And the last one, which I'm going to put above here because I ran out of room, is that the 0 vector dotted with A should obviously give you 0. So that's 0 vector, that's 0 number. Alright, now let's move to something that's more interesting, and that's some geometric properties of the dot product. So the first thing we need to remember is our law of cosines. Law of cosines. So if we have a triangle, and we'll say this is side A, length A, this is length B, actually I'm not, and that's length C, then, and this is the angle theta between A and B, then we can find the length C. C squared is equal to A squared plus B squared minus twice AB cosine of theta. Alright, so that's something that we need to remember from our earlier days. Alright, so if we have 2 vectors, we'll say vector A and vector B, and there's theta, the angle between them, then we can remember from before that this vector right here is A minus B, alright, with my arrows. Alright, now we can apply the law of cosine to the magnitudes of these vectors, and what we get is that the magnitude of A minus B squared is equal to the magnitude of A squared plus the magnitude of B squared minus twice the magnitude of A times magnitude of B times cosine of the angle between them. Alright, now if we remember what our properties were, let's just go back really quickly. This one right here I told you was going to come up a lot. We're going to use that here. And so A minus B, that vector's magnitude squared, is A minus B dotted with A minus B. And now we can apply our distributive property, and we get the magnitude of A squared minus twice A dotted with B plus the magnitude of B squared. And so that's what the left hand side is equal, and here's our right hand side. So canceling appropriately, we get that minus 2 2 times the dot product of A and B is equal to minus 2 times the magnitude of A with magnitude of B times cosine of the angle between them. So, if we divide both sides by minus 2, we get that the dot product is equal to the magnitude of A times the magnitude of B times cosine of the angle between them. So we defined the dot product as such, and we discovered based on that definition that this was actually true. That we could get the dot product by finding the magnitudes of A and B and the cosine of the angle between them. Now that can be useful for several reasons. One, if we're trying to find the angle between them, then we can just solve for cosine of theta, which is equal to the dot product, divided by the magnitude of A and the magnitude of B. So this is just another way to write that same thing, except this time we're solving for cosine of theta. Okay? Let's stop here for now.